Total variation distance is really well adapted to discrete random variables, taking values in the same countable sample spaces. For example, Bernoulli random variables and Poisson random variables. In that context, one of the main places that it's useful is in the following law of rare events, which is a quantitative version of what's often called Poisson approximation. Let x1 through xn be independent Bernoulli random variables with potentially different means, p1 through pn, and consider the sum of those. If all of the p's were equal, this sum would be a binomial distribution with parameters n and p, but for different pj's, it's just a sum of independent things. The convolution of these different Bernoulli distributions in distribution. We're going to compare that sum to a Poisson distribution whose mean is the sum of the means, p1 through pn, of those Bernoullis. The fact of the matter is that if those pj's are all sufficiently small, the sum of those Bernoullis is very close to that Poisson. In fact, it is close in total variation distance. The total variation distance between the sum, Sn, and the Poisson, n, is less than or equal to the sum of the pj squared. This gives us an immediate proof of what's often included in undergraduate probability courses as the Poisson approximation. That is, if we have a parameter lambda bigger than 0, we take Bernoullis with probability lambda over n, of course meaning that we have to have n large enough so that that's less than or equal to 1, then the binomial distribution of parameters n and p equals lambda over n is close in distribution to the Poisson of parameter lambda, closer and closer as n grows. And that's just because this binomial is equal in distribution to the Sn above in the case where all of the pj's are equal to lambda over n. And therefore, in that case, the theorem tells us that the total variation distance between that binomial distribution and n, which is a Poisson of parameter lambda, is less than or equal to the sum of the pj squareds, which is going to be lambda squared over n. And that, of course, goes to 0 as n goes to infinity. Here is a nice demonstration of the simple Poisson approximation of binomial distributions. Overlapping here, we have the probability mass functions displayed for a Poisson distribution in blue and a binomial distribution in red, with parameter n being 100 and p being 1/10 for the binomial, and total parameter lambda being n times p for the Poisson. We can vary these parameters to see that for large n, as p stays fixed, the approximation is really quite good. On the other hand, if n is not sufficiently large and p is large, the approximation is not very good. So the law of rare events really applies in the case where p is small and n is large. We're going to present two proofs of this law of rare events in this lecture. The first is very straightforward and computational based on the calculations we did at the end of the last lecture and one of your homework problems, which is the following lemma about how total variation distance interacts nicely with convolution of probability measures on Euclidean spaces. If I have probability measures mu1 through mu(n) and nu1 through nu(n), all Borel probability measures on a fixed Rd, then the total variation distance between the convolution of the mu's and the convolution of the nu's is less than or equal to the sum of the total variation distances between each of those terms down the line. You're going to prove that on a homework set. Using this nice calculation, we can leverage the calculations of total variation distances between Bernoullis and Poissons that we did at the end of the last lecture to prove the law of rare events quite quickly. That is, if we let nj be a Poisson random variable of parameter pj, and let n1 through n little n be independent, then we can compare those to the Bernoullis x1 through xn that are independent, which is what we're trying to estimate. the total variation distance between Sn and n, is going to be the same as the total variation distance between Sn, which is the sum of those, and the sum of these Poissons, because as we showed in an earlier lecture, a sum of independent Poissons is Poisson, with parameter being the sum of the parameters. And the n we're supposed to be using here is indeed Poisson, whose parameter is the sum of the pj's. Well, the x's and the n's are all independent, and so the law of x1 through xn is the convolution of the laws of the x's. The law of n1 through nn summed is the convolution of their laws. And so by the definition of total variation of random variables, which is just the total variation distance of their laws, this is the total variation distance between the law of x1 convolved with the law of x2 convolved with the law of xn, and the law of n1 convolved with the law of n2 convolved with the law of n, little n. By the above exercise from your homework, this is less than or equal to the sum of the total variation distances between the xj's and the nj's. Those are Bernoulli's and Poisson's, each of parameter pj, and we calculated last time that that distance is exactly equal to p times 1 minus e to the minus p. And to complete the proof, we just need to see that that's less than p squared. Well, notice that 1 minus e to the minus p can be written as the integral from 0 up to p of e to the minus x dx. And since e to the minus x is less than or equal to 1, this is less than or equal to the integral from 0 up to p of dx, which is, of course, p. And so that shows that this is less than or equal to p squared, which completes a proof of this law of rare events. Now, you might find that proof a little unsatisfying for a few reasons. First, it really relies heavily on this computation here, which we didn't do here. You're going to do it on your homework. The proof there might also not give you too much intuition since it's an induction proof. So I'd like to take some time now to give a different flavor proof of this same result and use this as an opportunity to introduce the concept of coupling. A coupling of two probability measures is really just a realization of those measures as the laws of two random variables on a common probability space. That is, given two probability measures on the same sample space, probability space, a coupling of those two measures is a pair of random variables, x and y, on a common probability space that have those measures mu and nu as their individual laws. We could also dispense with the idea of random variables and just consider a coupling to be a joint law. That is, we're just finding some measure on the product space whose marginal distributions are mu and nu. Now, as you can imagine, there are generally zillions of couplings of two probability measures, although that's not always true. I suggest that on the back of an envelope you work out why it is that if the two measures are just single point masses, there's only one coupling of them. And it's this silly coupling here. We can always couple two probability measures by taking their product measure. In other words, we realize the two by taking independent random variables with those two laws. We know we can do that quite easily. In fact, we know from Kolmogorov that we can do it with an infinite sequence of them. But usually that's not an interesting coupling. Usually we want to get some information by constructing a coupling that is adapted to a problem that we're interested in. Now, what does this have to do with total variation distance? Well, here is a coupling estimate, which shows us how we might be able to use adapted choices of couplings to find good bounds on total variation distances between measures. If I take two probability measures mu and nu on the same sample space, and I construct any coupling of those two measures, then the total variation distance between them is bounded above by the probability that x is not equal to y in that coupling. Let's prove this. Fix any Borel set in the real line, which is where these two random variables x and y live, and we just compute that the distance between mu of b and nu of b is the difference between the probability that x is in b and the probability that y is in b. Of course, that's the same thing as the expected value of the indicator of b evaluated at x, which is nothing other than the indicator of the set where x is in b. minus the indicator of b evaluated at y. We use the triangle inequality for integrals to write that as less than or equal to the expected value of the absolute value of the difference between those two indicator functions. Now, we've seen before that if we take the absolute value of the difference between two indicators, that is the indicator of the symmetric difference between those two sets. Now, for any set B, the symmetric difference between the sets x in B and y in B is certainly contained in the set where x is not equal to y. Indeed, the difference here is a set of points where y is not in B but x is, and the reverse difference here is a set of points where y is in B but x is not. So for any outcome in this symmetric difference, x is not equal to y. Therefore, this expectation is less than or equal to the expected value of the indicator of the set where x is not equal to y, and that is exactly equal to the upper bound we were hoping to prove here. Let's see how we can use this coupling estimate to give a more adapted proof of the law of rare events. So we have our independent Bernoullis of parameters pj, and we want to compare their sum Sn to a Poisson of rate given by the sum of the parameters pj. We're going to do that by constructing a coupling of these two laws. Right now, there's no relationship between these two random variables given. We don't even have them constructed on the same probability space. We're just talking about the distributions. So we want to realize those two in the same probability space somehow, and then use the coupling estimate to give a bound on the total variation distance between them. So here's how we're going to do that. We'll fix some ambient probability space, omega fp, that supports n independent uniform random variables. By Kolmogorov's extension theorem, or much simpler things, we can of course construct such a probability space easily. And we're going to use those UJs to construct both Sn and n. Here's how. For each UJ, let's take the following indicator function of it. The indicator of the interval from 1 minus pj up to 1, open on the left, closed on the right, of uj. We'll call that zj. This is a 0, 1 valued random variable, and let's just compute the probability that it takes the value 1. That's the probability that uj is in the interval from 1 minus pj up to 1, but this is a uniform random variable on the unit interval, and so that probability is just the difference, 1 minus pj, which is pj. In other words, zj is a Bernoulli random variable with parameter pj. It has the same distribution as xj. Great. Now we'd like to construct random variables mj that are Poissons of parameters pj on the same space, using the same random variables uj. And the way we're going to do that is as follows. For each j, we let alpha j be the cumulative probability mass function of a Poisson of rate pj. That is, it's the Poisson measure of the set from 0 up to k, which is the sum of e to the minus pj, pj to the L over L factorial. And just for convenience, in the summation notation we're going to use in a moment, we define alpha j of minus 1 to be 0. Now let's define mj to be the sum of k times the indicator of the set where uj is in between alpha j of k minus 1 and alpha j of k. Why are we doing that? Well, of course, in this sum, if we go from k minus 1 up to k only, that last term, we get the probability mass function of a Poisson. And that's supposed to be the place where the Poisson takes the value k. And so this, in fact, exactly constructs a Poisson random variable out of the uniform random variable. Let's just check that. The probability that mj is equal to k is exactly the probability of this event here for that fixed k. Again, using the definition of the distribution uj, that's just equal to the difference between the two endpoints of that interval. which is e to the minus pj, pj to the k over k factorial, which is indeed the probability mass function of a Poisson. And so we see that indeed mj is Poisson of rate pj. Now, the uj's are independent, and we've constructed both the xj's and the mj's to be functions of each individual uj. And so that means that the xj's are independent from each other, and the mj's are independent from each other. The x's and the m's are not independent of each other, however. So in this coupling, we have not made the boneheaded independent coupling. We actually have some correlations between the x's and the m's. And it's those correlations that are going to give us the estimate that we need. So let's let t be the sum of the z's, and let's let m be the sum of the mj's. So this, of course, has the same distribution as our original Sn. And this, because a sum of independent Poissons is a Poisson whose rate is the sum of the rates, is the same in distribution as our original n. So if we want to compare the total variation distance of these, we can use these realizations and then apply our coupling estimate. So the total variation distance between Sn and n is less than or equal to the probability that the sum t is not equal to m. Now, how do we estimate that? Well, we notice, of course, that the event that each term zj is equal to mj for all j, the intersection of all those events, is contained in the event that t is equal to m. If all the terms here are equal to all the terms there, then the sums are the same. And that means, contrapositively, that the event in question, that t is not equal to m, is contained in the union of the sets where zj is not equal to mj. And therefore, by the union bound, the probability here is less than or equal to the sum of the probabilities that zj is not equal to mj. Now, how can zj not equal mj? We're looking at the probability of the event that this indicator is not equal to this sum of indicators, which is, of course, the event that we get one of the terms here with k bigger than or equal to 1, or in the case where k is equal to 0 or 1, this bound differs from this one, and the amount they differ, because this is a uniform random variable, is going to give us our probability. That is, looking at this picture here of the cumulative distribution function of zi versus mi, these two differ precisely here and here. And by the uniform distribution that we're using here, that probability is therefore equal to this, which we can work out now actually very similarly to the calculations at the end of the previous less motivated proof, is equal to that, which simplifies, as we showed before, to pj times 1 minus e to the minus pj, and as we calculated, that's less than or equal to pj squared, giving us a motivated proof of where those calculations came from. Now notice that we've made what may be a very boneheaded estimate right here. This might actually be quite a bit smaller than this sum a priori. We haven't actually utilized the correlations between the z's and the m's other than between zj and mj. And that's the beauty of coupling arguments. You can always try to do better by choosing a more clever coupling or by utilizing more details about the coupling in order to get a better estimate. Because of that insight, couplings are a very ubiquitous tool used in lots of different areas of probability theory. In particular, in large deviations problems, in optimal transport, in stochastic analysis, and in other fields that you may decide to go and study after you finish this full-year course. And I just wanted to give you a tiny taste of where couplings come into some basic constructs that we're not really going to use, but you may want to be aware of going forward. As I've noted, total variation distance may not be the right choice of a distance function for problems that we're interested in, for reasons that we'll see in the next lecture. So here is a different set of metrics on probability measures motivated by coupling arguments that may be more useful in many settings. we have to restrict our attention a little bit here. Let's look at the set of probability measures that have a finite pth moment. That is, we're talking about probability measures on Euclidean space for which the function x to the p is integrable for some p bigger than or equal to 1, or actually bigger than 0 would be fine for this definition as well. On that space of probability measures, we can define a distance function called the p-Wasserstein distance between two such measures as follows. We take any coupling of those two probability measures, so we construct a pair of random variables having those as their marginal distributions, and we take the LP distance between those two to the pth power. Then we take the infimum of that over all possible couplings. That gives us what's called the LP-Wasserstein distance. And for each p, it does define a metric on the space of pth moment probability measures. This distance is, generally speaking, weaker than the total variation distance, although you have to make further restrictions to actually get some kind of inequality between the two. We are not going to study Wasserstein distance anymore in this course. It will not come up. It would come up in advanced topics that come after this full year course. We will, however, shortly be studying a notion of convergence of probability measures which is metrized by this in addition to other distance functions. And so that is a good lead-in for our next topic, which is weak convergence, or convergence in distribution.